Hello everyone. So today is the next class of the probability distribution. Specially we'll focus on the examples of probability distribution, different types of examples. In this lecture we'll talk about some examples on especially discrete distributions, some real life problems maybe, and how to deal with the problems of that. So in the previous video you have learned about the different distributions, binomial, Poisson, geometric distribution, and also some continuous distribution, normal distribution, uniform distribution, gamma distribution, beta distribution. So lots all. So now we'll talk about some examples on that, typically some examples on this video. So let us have first one, the problem number 1. Look at that, it belongs to the discrete distribution. Two coins are tossed, find the probability distribution of the number of heads. So we'll start with a very simple problem. Actually, two coins are tossed, find the probability distribution of the number of heads. In this case the event space is given by omega is given by head head, head tail, tail head, and tail tail, right? So this is the event space. Now where H denotes the head and T denotes the tail, outcome tail. So let us define the random variable. We have to define, before we going into the distribution, we have to define the random variable. So in this case, if we write, let x be the random variable, let x be the random variable denoting the number of heads, denoting the number of heads. I'm writing number of heads, it denotes the number of heads, right? So let x be the, so in every problem of distribution you have to define the random variable x be the random variable denoting the, in this case your x is the random variable denoting the number of heads. Then the spectrum of x is given by, spectrum of x is 0, 1, 2, right? Because you can have 0 heads, 1 head, or 2 heads, right? So these are the possibilities. So in this case you can write 0, 1, 2 is the spectrum of the random variable. Okay, and you can calculate that probability of x equal to 0, that is no head. X equal to 0 denotes the probability of no head, that is equal to 1/4 probability of, that is from the classical rule. Okay, and x equal to 1, that will give you 2/4, because you have two cases where you have one head, 1. Okay, look at that, the event space, and probability of x equal to 2, that will be 1/4, that is 2 heads. Only one case you have, that is 2 heads. So now you can write the distribution function, probability distribution. So I equal to, the spectrums are given by I, 0, 1, 2. These are the possible values of the spectrum I. And what are the probabilities? Probability of x equal to I, that is equal to 1/4, okay, half, and 1/4. So this is the required probability distribution. This is the probability distribution of a discrete random variable. Okay, so you can take it as a box, you can write in a table format. So this is the probability distribution, and x equal to 0 represents the no head, x equal to 1 represents 1 head, and x equal to 2 represents 2 heads. So that is the importance, and that is the significance of that writing of this in form of probability. Okay, so we have started with a very simple example. Now let's move to another example. 5 balls are, example 2, 5 balls are drawn from an urn containing 3 white and 7 black balls. Find the probability distribution of the number of white balls drawn without replacement. So you are not giving back the ball which is drawn without replacement. This is not with replacement, this is without replacement. So your urn contains actually 3 white balls and 7 black balls. That is the problem, and you are drawing a ball one by one. Find the probability distribution of the number of white balls. Okay, so in this case also, first you have to define the random variable. Let x be the, in this case what is your random variable? X be the random variable denoting the number of white balls. Once again, let x be the random variable. You have to write that in your problems. Random variable denoting the number of white balls. Okay, white balls. So what is the spectrum? White balls drawn from the urn without replacement. You have to write also without replacement, drawn from the without replacement. So what is the spectrum? What is the spectrum of the random variable in this case? Again you have to write the spectrum. These two things are very important in discrete distribution. In all the distributions you have to write the x. Spectrum of x is, what is the spectrum? Spectrum is 0, 1 and 2 and 3, because the maximum number of white ball is 3. Number of white balls is 3, so spectrum will be 0, 1, 2, 3. Okay, now let us calculate probability of x equal to 0. Probability of x equal to 0 means you are drawing no white balls. There is no white balls. So how many balls you are drawing? 5 balls you are drawing. 5 balls are drawn. Okay, 5 balls. Look at that, 5. So all 5s are black if you are not drawing the white balls. So it will be 7c5. Just like using the classical rule, you can calculate the probability. And total number of ball was 10. So 10c5. And if you calculate, this will be 1 by 12. Okay. Next, probability of x equal to 1. That is, you are drawing 1 white ball. So it will be 3c1. Out of 3 white balls, you are drawing 1 white ball. And out of 7 black balls, you are drawing 4. So that makes 5. So out of 10 balls, you are drawing 5 white balls. So if you calculate, this will be 5 by 12. Actually, I have calculated. Next, probability of x equal to 2. Similarly, you can calculate. That means that you are drawing 2 white balls. So that will given by 3c2, 7c3 by 10c5, right? And that is equal to 5 by 12. Once again, if you calculate, you will get that, because 7c4 is equal to 7c3 and 3c1 is equal to 3c2 using the combination rule. Next, last one, probability x equal to 3. That means all 3 are white balls, 3 white balls. So it will be 3c3 and 7c2, right? And that will be given by 10c5. And that is equal to 1 by 12. That is equal to 1 by 12. So this is the thing. Now you can write the distribution. If you write the spectrum, I denote the spectrum points 0, 1, 2, 3, and probability of x equal to I, probability at that point, that is given by 1 by 12, 5 by 12, 5 by 12 and 1 by 12. Okay, you look at that, sum of the probabilities is equal to 1. So that is verified also. And this is the probability distribution. If you write in a table, it will denote the probability distribution. So that is how you can express the problems of probability in terms of probability distribution using the discrete probability distribution. Actually, we are talking about. So this is the problem. Let's now move on to more problems in this lecture. Let's have we have a spectrum of the random variable x. Next, number 3. Spectrum of the random variable x consists of the points 1 to n. So spectrum of the points are random variable x are given by 1 to n points, and probability of xi, probability of x equal to I, is proportional to 1 by I into I plus 1. So determine the distribution function of x and compute these probabilities. So that is the problem. So already spectrums are given in the problem, and probability of x equal to I is given as proportional to 1 by I into I plus 1. So we can write in this case probability of x equal to I equal to k for some constant. K is a constant, k into I by 1 by I into I plus 1, right? So this is the probability of x equal to I. Okay, so this is the probability. Now we know that for a possible PMF, probability mass function, we must have summation I equal to 1 to n, probability of x equal to I equal to 1. This is the condition for a possible PMF. So if you apply this, then I equal to 1 to n, k into 1 by I into I plus 1 equal to 1. Okay, now k summation k into summation I equal to 1 to n, we can write is this as a partial fraction 1 by I minus 1 by I plus 1. In terms of that, we can manipulate that. This is an algebraic manipulation. You know that this is called partial fraction. So this is equal to k into, if you take the summation, alternative terms will be cancelled and you are remain with 1 minus 1 by n plus 1. Okay, because you look at that, I equal to 1 minus half, I equal to 2, it will be half minus 1/3, so on. So alternative plus minus sign will be cancelled and you are remain with 1 minus 1 by n plus 1 equal to 1. From this you can calculate the value of k, and the value of k will be n plus 1 by n. This is the value of k. Okay, so we are applying the condition of the possible PMF, that is sum of the probabilities equal to 1, and that gives you the values of k. Okay, now what do you have to calculate? You have to calculate the distribution function of x. Okay, now let f be the distribution function, and for x less than 1, let f be the distribution function, and for x less than 1, you can write fx equal to probability of that definition of distribution function, that is summation, you can take minus infinity to 0, that will be give you 0, because for less than 1 there is no point, spectrum points, and for I less than equal to x less than I plus 1, you will have I equal to 1 to n minus 1. Okay, and fx is given by fx equal to summation alpha equal to 1 to I. Okay, and probability of x equal to alpha, that is from the definition of the distribution function, and that is equal to k into summation alpha equal to 1 to I 1 by alpha into alpha plus 1. Okay, and you know the values of k. Values of k is actually n plus 1 by n. So if you substitute and if you simplify again the previous, like this calculation, this how you have calculated the k, this calculation, similar calculation, and that will give you n plus 1 by n into I by I plus 1. Alternative terms will be cancelled, and this is the fx. This is the distribution function in this range. This is the distribution function in this range. Next, if it is for x greater equal to n, more than that, again you have fx equal to, you can calculate, that will be equal to 1. Okay, so finally your distribution function is given by, will be given by fx equal to, let me summarize the distribution function. Fx is equal to 0 when x less than 1, equal to n plus 1 by n into I by I plus 1 if it is lies between x is lies between I less than equal to x less than I plus 1. I runs from 1 to n minus 1, right? Okay, and equal to 1 if it is greater than 1, greater equal to n, sorry, because n greater equal to n, so it will n. This is already verified. Now this is the distribution function. Okay, this is the distribution function already calculated. Now look at the problem. You have to calculate the probability 3 less than x less than equal to n. So let me calculate the probabilities. Probability of 3 less than x less than equal to n, that will be calculated by fn minus f3 using the properties of distribution function. Already we have the lecture in my previous videos. Fn minus f3, so fn is 1, okay, because from the definition of distribution function, and f3 is given by n plus 1 by n into what is your f3. F3 is, you are using this range, you are using this one, this value, I by I plus 1, so 3 by 3 plus 1, that will be 3 by 4, that is 3 by 4. So that is equal to, if you calculate, n minus 3 by 4n, sorry, this will be n, this is your n, okay, 4n. Okay, this is, and another probability you have to calculate, probability of x greater than 5, that can be calculated by 1 minus probability of minus infinity less than x less than equal to 5. We can write this. You can calculate probability of x greater than 5, that will take a lot of steps, but we can calculate by the complementary, using the complementary part. So 1 minus probability of minus infinity less than x less than equal to 5, and that will give you 1 minus probability f of 5, distribution function f of 5. And f of 5, this is from the definition of the distribution function. Probability of minus infinity less than x less than equal to small x is fx, and f5 is given by this one. You are using n plus 1 by n, 5 by 6, so that is equal to 1 minus n plus 1 by n into 5 by 6. So you can calculate that the value will be n minus 5 by 6n. Okay, clear? So this is how you will solve the problems on discrete distribution, especially the spectrums are given, you have to find out the distribution function. So I gave you the way how to find out the distribution function. Before that, if you want to find out any arbitrary constant in the equation, for you can use the conditions for a possible PMF, that PMF is fi is greater or equal to 0 for all I, and summation will be equal to 1. Let's move to the next problem now. Yeah, so let's have another example, practical example of discrete distribution, real life problems. Each sample of water has a 10% chance of containing a particular organic pollutant. Assume that the samples are independent with regard to the presence of the pollutant. Find the probability that in the next 18 samples exactly 2 contain the pollutant. Determine the probability that at least 4 samples contain the pollutant. So let me first tell you the first part. Find the probability that in the next 18 samples exactly 2 contain the pollutant. So this type of problems, how will you deal with this type? So obviously you have to write the random variable. Okay, so this type of problems basically is you look at the problem very carefully. There are the chances of pollutant and or non-pollutant. So you have a case of failure, non-failure, success, this type of case, success, failure, head, no head, 6, no 6, this type of problem. So we are specially dealing with this type of problems in binomial distribution, right? So let me give an example, few examples. on binomial distributions first? Yes, I have that binomial distribution. So these are the random experiences. Suppose you flip a coin 10 times. Let x be the number of head of tens. X number of heads of 10. So this is the use of you have to use the binomial distribution. Our own machine tools produces 1% defective parts. Let's x be the number of defective parts in the next 25 parts produced. So this is also an example of binomial distribution. Next, each sample of air has 10% chance of containing a particular rare molecule. So let x be the number of air samples that contain the real molecule in the 18 sample analyzed. Also, you have a 4 of all bits transmitted through a digital transmission channel, 10% are received in error. So let x be the number of bits in error in the next 5 bits transmitted. So these are the examples of binomial distributions, the real life situation. And also you have a another example. We have more examples on that. A multiple choice test contains 10 questions, each with 4 choices, and you guess at each question. Let x the number of questions answered correctly. Okay. In the next 20 births at a hospital, let x the number of female births. And of all patients suffering a particular illness, 35% experience improvement from a particular medication. So you want to test that medication. In the next 100 patients administered the medication, let x be the number of patients who experience improvement. So these are the applications. Okay, you can apply your binomial, because it may be success, it may be failure. So that binomial distribution is classified into success, failure in this way. So in this problem, let me analyze. Let x be the number of samples that contain the pollutant in the next 18 samples analyzed. So your chances are 10%. So what is the probability of success? Probability of success is given by 0.1. 10 by 100, that is equal to 0.1. And what is n? N is equal to 18. Okay. Now exactly 2 contains the pollutant. So you have to calculate. X is already defined. You have to define x. So x follows binomial distribution with n 18 and probability of success 0.1. This is called the, so this is the meaning of that. X is a binomial NP variate. X is a binomial NP variate. N is 18 here and P is 0.1. Okay. Now you have to calculate exactly 2 contain the pollutant. So probability of 2 successes, that is probability of x equal to 2 equal to 18C2 and 0.1 whole square, and your failure is 0.9. 1 minus probability of success equal whole to the power 16. So this is the calculation. You can calculate that with your calculator. This will give you the value of the probability for exactly 2 successes. And next one is that determine the probability that at least 4 sample contain the pollutant. At least 4. At least 4. So in this case you have to calculate probability of x greater than or equal to 4. So you can calculate like probability of x equal to 4, x equal to 5, x equal to 6 until 18. So it's better to calculate the complementary part, that is probability of x 1 minus probability of x less than 4, and that will be equal to 1 minus probability of x equal to 0, x equal to 1, probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to 3, this way. Okay, you can calculate like this, and you can calculate the probabilities, and you can check the probabilities, approximate value of the probabilities using this distribution, because your probability x equal to 0 will be 18C0, 0.1 to the power 0, 0.9 to the power 18, like this you have to calculate. So this is how you can deal with the discrete probability distributions, that is the binomial distribution I was talking about. Okay, and lot of examples of binomial distributions, real life problems. Next I will give you the idea of the geometric distribution. Already I gave you the distributions definition of the geometric distribution. Let us have once more. In a series of Bernoulli's trials, independent trials with constant probability p of success. Obviously, Bernoulli's trial, actually binomial distribution also is a Bernoulli sequence, and it is probability of success is always constant probability success. Let the random variable x denote the number of trials until the first success. Look at that, x denote the number of trials until the first success. Then x is a geometric random variable with parameter p, and it is given by 1 minus p, that is q is actually failure is q equal to 1 minus p whole to the power x minus 1, x equal to 1 to 3, etc. The spectrum points into p. This is the geometric probability distributions, and this is your actually discrete. Now let us have an example on that. The probability that a wafer contains a large particle of contamination is 0.01. Okay, it is assumed that the wafers are independent. What is the probability that exactly 125 wafers need to be analyzed before a large particle is detected? Detected. Okay, so look at that, already the probability success is given. If you define the contamination, a large particle of contamination as the probability of success, then p equal to 0.01. You can define p equal to 0.01 and n is equal to 1 to 5. Okay, so you look at that. Let x denote the number of samples analyzed until a large particle is detected. Let x denote the number of sample size. So you have to define, always in the distribution problem, you have to define the probability of random variable, that is the x, capital X denote the number of samples here analyzed until a large particle is detected. And then x is a geometric random variable with p equal to 0.01. Then the required probability is given by probability of x equal to 125, and that is equal to 0.9912. Using the geometric probability distribution, 1 minus p whole to the power x minus 1, okay, into p, x equal to 1 to 3, etc. In this case your x is 125. Okay, this is your x actually. This is your x. So 0.99 to the power 124 into 0.01. So you can calculate the probability using a calculator. So this is how you can apply that you are getting the first success before the failure. So until the trials until the first success. Okay, let x denote the number of trials until the first success. This is how you can use your geometric probability. Next, let's have another interesting problem. If there is a war every 15 years on the average, then find the probability there will be no war in 25 years. This is a different type of problem. So it is given that there is a war in every 15 years on the average. Average is given. Find the probability that there will be no war in 25 years. So before we solve the problem, let us define what is stochastic process. A very important concept, right? Let xt be a random variable. X is a function of t. X is a random variable depending on a real variable t. Actually real life problems, actually time, t is the time in real life problems. A given set of random variables xt, t belongs to the even space where where omega is the given subset of real number, is called a stochastic process. Okay, a given set of real variables, that is called the stochastic process. Actually xt is a function of real variable t, and the t is the actually represents the time in real life problems. Okay, and there is a theorem, number of changes of a stochastic process in a given interval of time follow Poisson distribution under certain conditions. So we learned that Poisson distribution is given by what is the spectrum of the what is the probability mass function of the Poisson distribution, e to the power minus mu into mu to the power I by factorial I, right? And spectrums are given by I equal to 0, 1, 2, etc. Okay, so number of changes of a stochastic process in a given interval of time. If you have an interval of time and there is a number of changes that follow a Poisson distribution under certain conditions, you can follow, you can see the theorem, but theorem is not proved here. In this video I am not proving the theorem, I am just giving the statement of the theorem. The number of changes in a stochastic process in a given interval of time follow a Poisson distribution. So this is the Poisson distribution. So let us how will you solve the problem? Let's once again see the problem. War in every 15 years on the average, and there will be no war in 25 years. So let us solve the problem now. Let us add a page here. So we take, you have to take the unit of time, right? We take 1 year excuse me, as the unit of time. Okay, we take 1 year as the unit of time, and here lambda equal to, suppose lambda equal to excuse me, lambda equal to number of changes per unit time on the average. Okay, and that is equal to, so you look at that, you take 1 year as the unit of time. You have to take the unit of time before you start the problem, and you have to define a lambda. What is your lambda? Lambda is the number of changes per unit time on the average. So what is the number of changes? What is the number? You look at that, there is a war in every 15 years. So lambda equal to 1 by 15. Right? Number of changes per unit time on the average, and that will give you 1 by 15, because in the question it is given that there is a war. You look at the problem, there is a war in every 15 years on the average. So lambda is equal to 1 by 15. Number of changes per unit time on the average. Okay. Now let us define x. Let x be the random variable. X be the random variable denoting the number of words in the interval. What is the interval? 0, 25. That is the interval, because it said that there is a no war in 25 years. So it will start from beginning and it will ends at 25. So your interval is 25 years, 0 to 25. Your interval is 0 to 25. Let x be the random variable denoting the number of words in the interval 0 to 25. Now then according to the stochastic process, the theorem on stochastic process, then x is Poisson distribution. You write here with parameter you look at that the parameter will be given by mu equal to lambda into t. And what is your lambda? Lambda is 1 by 15 and t is equal to 25. Okay, and that will give you 3 by 5. This is your parameter of the Poisson distribution mu. This is how you will calculate. So first you have to take 1 year as the unit of time, and you have to define lambda, that is the number of changes. It can be anything. In this case it is war. It can be radioactive elements per unit time it's emerging from a particle. It can be any process, number of phone calls in an interval. So there are so many processes, all are stochastic processes. So let's x be the random variable denoting the number of words in the interval 0, 25. Then x is a Poisson distribution with parameter mu equal to lambda t, and that is given by 3 by 5. Okay, therefore it is given that there will be no war in 25 years. You look at that, there will be no war. So probability here I equal to 0. So probability of x equal to 0, that is it represents no war in 25 years, and that is calculated by e to the power minus mu into mu to the power 0 by factorial 0, and that is given by e to the power minus 3 by 5. You can calculate using the calculator or any other process. So this will be the probability. Okay, clear? So this is how you can use your stochastic process, and this represents the actually follow the Poisson distribution. Let's have another problem to understand the thing. A radioactive source, just I was talking about that it can be a radioactive source, it can be a number of phone calls in a particular booth. So you have a radioactive source emits on the average 2.5 particles per second. So it is given that lambda equal to 2.5, right? I'm not defining, you have to write the same statement, same concept. You have to write lambda is the number of changes per unit time on the average, and that is equal to 2.5. It is clearly given per second, and your unit time is per second. 1 second is the unit time, right? 1 second as the unit time. You have to write 1 second as the unit time, and lambda equal to number of changes per unit time, and that is equal to 2.5. Let x be the random variable. Let x be the random variable denoting the number of particles emitted in the interval. Okay, you look at that, calculate the probability that 3 or more particles will be emitted in an interval of 4 seconds. So here you can write let x be the random variable, x be the random variable denoting the number of particles you have to write in every problem x, very very important step, emitted in the interval. What is the interval? 0, 4, right? In 4 seconds, 0, 4. So how will you calculate? So 0, 4. So lambda is defined, x is defined. Now what is your parameter? Poisson distribution. X follows Poisson distribution with parameter. X follows Poisson distribution with parameter mu, and mu is given by lambda t, right? And lambda is your 2.5 into t is your 4. So it is equal to 10, right? This is equal to 10. Okay. Now you have to calculate the probability that 3 or more particles. So you have to calculate probability of x greater equal to 3, x greater than or equal to 3, and that is equal to 1 minus probability of x less than 3. 1 minus probability of x less than 3, and that is equal to 1 minus probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2, right? And that is equal to, you can calculate the probabilities, 1 minus e to the power minus mu to the power 0 by factorial 0 plus e to the power minus mu into mu to the power 1 by factorial 1 plus e to the power minus mu into mu square by factorial 2, and so, and this is the last. Okay, because it's better to have a complementary part always. So you can simplify, and you can see the result will be minus 1 minus 61 e to the power minus 10, because your mu is 10 already calculated. So this is how you can deal with the problems of Poisson distribution. So in this lecture you have learned how to deal with the problems of binomial distribution, geometric distribution, and Poisson distribution. Also you have a concept of the stochastic process, how to deal with the problems of stochastic process, and stochastics process is actually follows Poisson distribution, and you have to how will you define lambda and how to define, and in every problem, last but not the least, in every problem you have to define x, the random variable. Okay, so follow my next video. My next video will be on continuous, some problems on continuous distribution. Thank you all of you.